Welcome to Jeremy's IT Lab. This is a complete course for the CCNP NCORE, Enterprise Core exam. This course will cover all topics you need to know to pass the NCORE exam. In this video, we will look at the High Availability feature SSO, Stateful Switchover, as well as other related features. In a device with multiple route processors, these features are used to keep traffic flowing when an active route processor fails over to the standby route processor. Here's what we'll cover. We'll cover SSO, Stateful Switchover. This helps keep interfaces up during a route processor failover. We will also cover NSF, Non-Stop Forwarding. It helps a device continue to forward Layer 3 traffic, even if a route processor fails. Then GR, Graceful Restart. This is similar to NSF. It helps traffic continue to flow, even if a route processor fails. NSF and GR are often confused with each other. Many people think they are the same thing. In this video, I hope to clearly differentiate between them. We will also cover NSR, Non-Stop Routing. NSR aims to maintain routing protocol adjacencies when a route processor fails. Of these four high availability techniques, SSO is the one explicitly mentioned in the NCORE exam topics, but you should know all of these. You don't have to necessarily know all of the technical details for NCORE, but you should be able to clearly differentiate between these four. That's my goal for this video. And watch until the end of the video for a bonus practice question from Boson Software's XSIM, my recommended practice exams for NCORE. In this video, we'll mainly be talking about chassis routers like this ASR 9010. However, the information in this video applies basically to any device with redundant route processors, a redundant control plane. This router, for example, has 2 slots for RSPs, and the route processor is a part of the RSP. With redundant control planes, we want the switch from active to backup to be as smooth as possible when the active one fails. However, it's easier said than done, and over the years, there have been different techniques that attempt to make that failover happen smoothly. First, let's see how a route processor failover would work without SSO, NSF, GR, and NSR, the topics of this video. During normal operations, adjacencies are established, for example, OSPF adjacencies. Same goes for Layer 2 protocols like STP, if these were switches. Traffic is flowing as normal. Note the names I've given these routers. P means provider, a service provider's router. PE means provider edge, a service provider's router that connects to customer equipment. And CE is customer edge, a customer's router that connects to the service provider. We'll see what happens when the PE router's RP fails. So there is a hardware failure on the PE router's active route processor. The PE router restarts, and adjacencies such as OSPF or BGP adjacencies go down. Traffic flow stops while the router reboots using the standby RP. After the failover and reboot, the adjacencies are finally re-established. However, traffic flow is still stopped as forwarding tables are rebuilt. The routers need to learn routes again, insert them into their routing tables, update their Ceph tables, etc. Finally, after minutes of downtime, traffic flow resumes. The former standby RP on the PE router is now active. So this situation is better than having no standby RP, in which case the router would just be dead if the active RP failed. But on routers and switches with separate and distributed control planes and data planes, ideally, a control plane failover would not affect the data plane. Traffic should still be able to flow through the line cards of the device. The purpose of SSO, NSF, GR, and NSR is to make that a reality, to improve this failover process. Before looking at SSO and the other features, let's look at a few other RP redundancy modes. These days, any device with multiple RPs should support SSO. So the ones we'll cover in this slide probably won't be used, but I think it will help illustrate how SSO evolved. First up is HSA, High System Availability. In HSA, during normal operations, the standby RP is down. If the active RP fails, the standby RP will reboot the router and take over as active. This is known as a cold restart. This is what I demonstrated in the previous few slides. The router has 2 RPs, which is better than 1, but there's no real coordination between the active and standby. So the failover process can take a long time, the time it takes for the router to restart. Then there is RPR, Route Processor Redundancy. You might remember this term from the switch stacking video. I mentioned it when talking about VSS. This is slightly different, since we're talking about redundant route processors in a chassis router or switch, not 2 separate switches stacked together. Anyway, during normal operations, the standby RP is partially initialized. The iOS image is booted. This is called a cold boot. The RP isn't totally running, but it's partially ready to take over for the active. The startup config is synced from the active RP to the standby RP when the standby RP boots. However, any changes to the system, for example, changes to the config, are not synced. Also, Layer 2 and Layer 3 protocols are not initialized on the standby. So, if the active RP fails, the standby RP reinitializes as active, reads the startup config, reloads the line cards, and restarts the system. This process is faster than HSA because the standby RP is already partially initialized with iOS cold booted. But still, failover can take a few minutes. These days, that is not an acceptable failover time. There is also RPR+. Same as RPR, during normal operations, the standby RP is partially initialized with iOS booted. And the startup config is synced from the active RP to standby RP. As an upgrade to RPR, in RPR+, config changes are synced from active to standby. But like RPR, Layer 2 and Layer 3 protocols are not initialized. However, a major plus is that there is no need to reload and reinitialize the standby RP and line cards. We still don't have a totally smooth transition from standby to active, but generally the failover time is 30 to 60 seconds. Okay, that's enough about these redundancy modes. Don't worry about memorizing the details of HSA, RPR, and RPR+. I just wanted to demonstrate how SSO evolved to provide some context for the rest of this lesson. Switching from an active RP to a standby RP seems like a simple thing, but it took some time before routers and switches were able to do it well. Now let's look at stateful switchover. SSO fully boots and initializes the standby RP. Note that SSO should be enabled by default on systems that support it, but if for some reason it's disabled, the command to enable it is first redundancy to enter redundancy config mode, and then mode SSO. With SSO enabled, when the standby RP is booting, a bulk synchronization is performed from active to standby. After that, incremental synchronization is used to sync any changes. This includes config changes, interface states, etc. By the way, this syncing of configurations and protocol states from the active RP to the standby RP is called checkpointing. And it also includes Layer 2 protocol states. Layer 2 protocols are initialized on the standby RP and their states preserved during failover. That includes things like STP, LACP, PAGP, VTP, port security, etc. Because these protocols maintain their states during failover, Layer 2 forwarding is maintained. There should be no traffic loss and no interface flaps, meaning the interfaces should remain up. That's fine for switches, however Layer 3 protocol states are not synced. So during failover, Layer 3 adjacencies go down, resulting in routes being cleared from the routing table. And without routes, Layer 3 forwarding is interrupted. Fortunately, the failover is faster than in the previous options, generally a few seconds depending on the device. So, SSO is much better than HSA, RPR, and RPR+. It keeps interfaces up, and Layer 2 forwarding is possible. But to maintain Layer 3 forwarding, we need the next technique. That is non-stop forwarding, NSF. NSF further optimizes SSO by allowing line cards to forward packets at Layer 3 while the RP fails over. This makes sense. These chassis routers use distributed Ceph. Their line cards should be able to forward traffic, even if the control plane is briefly lost. Note that NSF is enabled by default on devices that support it if SSO is enabled. NSF can't be configured. Now, there are some configurations in Cisco IOS called NSF, but they actually aren't NSF, they're something else. I'll explain that later. So, NSF achieves this because the fib is initially transferred to the standby RP during initialization, and then actively updated when there are changes. So to summarize NSF, it is the process of checkpointing the fib from the active RP to the standby RP, and therefore maintaining layer 3 forwarding on the device. However, routing protocol adjacencies are still interrupted. So that's a problem. Although the local device can still forward packets, neighboring devices will drop routes via this device when the adjacencies go down. So the layer 3 traffic flow is still interrupted, even though the local device is still capable of forwarding packets. To really preserve the traffic flow, we need the next technique. Before looking at that, let's cover a common misconception. NSF is a function of the local device. It does not require cooperation with neighboring devices. This is different than what many other resources say about NSF. That's because they are confusing NSF with the next topic, graceful restart. There's a good reason that people mistake the two, which I'll explain soon. So let's see how graceful restart completes this puzzle of maintaining traffic flow during failover. Graceful restart allows peers of a device performing an RP failover to maintain their routes via that device, even if the routing protocol adjacency has been lost. Normally, if a neighbor goes down, a router will remove all routes learned via that neighbor, but not with GR. They will keep sending packets to the device, even though the neighbor is lost. And the length of time neighbors will continue forwarding traffic is called the grace period. So, GR in combination with NSF maintains layer 3 forwarding during an RP failover. However, GR isn't something done only by the device doing the failover. The failing device does the graceful restart, but it depends on the other devices to give it that grace period and not remove the routes from their routing tables. Devices can be GR capable or GR aware, or both. The device failing over must be GR capable. It must be capable of doing a graceful restart. Then the neighboring devices must be GR aware. They must be able to keep forwarding traffic while the neighbor restarts. So this completes the puzzle. SSO maintains interface and layer 2 protocol states on the failing device. NSF maintains layer 3 forwarding on the failing device, and GR allows the neighboring routers to keep forwarding traffic to the failing device. Now let me clear up that confusion about NSF and GR. You may often hear the terms NSF capable and NSF aware. They actually mean GR capable and GR aware. They are just mixing up the terms. However, there is a good reason for that confusion. Cisco used the term NSF early on to refer to GR, perhaps before graceful restart became a common term. And Cisco still uses the term NSF in the configuration commands for internal gateway protocols. For example, in OSPF configuration mode, there is an option to configure NSF. That's graceful restart. And EIGRP, that's also graceful restart. And ISIS, that's also graceful restart, not NSF. In BGP, however, they do use the technically accurate term graceful restart. As well as in LDP, Label Distribution Protocol. That's a protocol used in MPLS. So I just wanted to point that out because you'll often hear the term NSF used, even though they're talking about graceful restart. That includes other study resources for the NCore, some of which I consulted while making this video. But there is a good reason for that confusion, because even the iOS CLI calls it NSF. So, next time you configure an IGP on a Cisco router, feel free to say, actually, that's graceful restart. Let's see how the failover process is improved using SSO, NSF, and GR. Because GR requires cooperation from neighboring devices, the devices make each other aware that they are GR capable, or at least GR aware, and able to help the neighbor if its RP needs to fail over. So, traffic is flowing as normal. Now, the PE router's active RP fails, and the routing adjacencies go down. Regardless, traffic forwarding continues as normal. Thanks to SSO and NSF, the PE router's line cards can still forward traffic. And thanks to GR, the other routers have no problem forwarding traffic to the PE router, even though the neighbor adjacency has been interrupted. Note that there is a risk to graceful restart. Even if the device is actually down, not just doing an RP failover, the other devices will continue forwarding traffic. If the devices are directly connected, they might detect physical links going down, but if they aren't, that could cause a problem. So it's important not to set the grace period too long. If the neighbor really went down, you don't want to keep forwarding traffic to it. Anyway, once the failover is complete, the adjacencies are re-established. Throughout the whole process, traffic continues flowing as normal. So, much better than the original example I showed at the beginning of the video. As a side note, the GR-aware devices helping the failing device are sometimes called helpers. You might hear the term helper mode. Just be aware of those terms. Okay, that's enough about GR for now. We have one more technique to cover. The final technique is non-stop routing, NSR. NSR attempts to maintain neighbor adjacencies during an RP failover. So it doesn't require cooperation from neighbors, unlike GR. The neighbors aren't even aware that an RP failover is happening. When using NSR, in addition to checkpointing the fib, routing protocol state information is also checkpointed to the standby RP. Routing protocol adjacencies and such should be maintained during a failover. Okay, so now we've looked at 4 different techniques. To maintain all forwarding during an RP failover, you need SSO and NSF, as well as GR or NSR. Enabling only one of the features isn't of much value. They work together. However, GR and NSR both aim to ensure neighbors continue forwarding traffic via this device during an RP failover. Keep in mind that you can't enable both at the same time for the same neighbor. You can use either, both achieve the same purpose. And keep in mind that these features don't make up for a bad design. Ideally, there should be redundant routers in the network, not just a router with redundant route processors. Let's see another quick example of RP failover, this time using NSR. Because NSR doesn't rely on other devices, there's no need to advertise NSR capability. When a failover happens, adjacencies are maintained. The neighbors are not aware of the failover. As a result, traffic forwarding continues as normal. Then, after failover, the traffic continues to flow as normal, and the neighbors are not aware there was a failover. Again, much better than the first example I showed in this video. Now I want to look at one particular case. That is SSO used in combination with HSRP. In this network, DSwitch1 and DSwitch2 are layer 3 switches with redundant route processors, and DSwitch1 is the HSRP active router. With SSO enabled, HSRP states are synced to the standby RP. If a failure occurs on the active RP, the standby RP will take over for the active RP. So a failover from the HSRP active, DSwitch1, to the HSRP standby, DSwitch2, is not necessary. Traffic from hosts in the network will continue to flow through DSwitch1. Of course, we are assuming DSwitch1 also has NSF and such enabled, so it can actually forward the traffic. Note that SSO HSRP is enabled by default when HSRP is configured. However, it can be enabled and disabled with this command, standby SSO from global config mode. Okay, we'll talk more about first-hop redundancy protocols like HSRP later in the course. I just wanted to point out this interaction between SSO and HSRP. And here's a chart summarizing the RP failover techniques we learned in this video. Ideally, you'll be using SSO and NSF, and either GR or NSR. For the NCORE exam, you should know the basic purpose of each of these, and be able to differentiate between them. SSO maintains interface and layer 2 protocol states. NSF checkpoints the fib from active to standby to maintain local Layer 3 packet forwarding. GR allows neighbors to continue forwarding traffic to the device during an RP failover. And NSR maintains neighbor adjacencies during RP failover. Okay, here's what we covered in this video. Failing over from the active RP to the standby RP sounds like a simple thing, but to do it smoothly, devices rely on a few different techniques that we looked at in this video: stateful switchover, nonstop forwarding, graceful restart, and nonstop routing. Okay, now let's go on to the quiz to test your understanding. And be sure to watch until the end of the quiz for a bonus question from Boson Software's XSIM for NCore. Here's quiz question 1. Which of the following features requires participation from neighboring devices? Pause the video now to think about the answer. Okay, the answer is D, GR. Graceful restart requires GR-aware neighbors that will continue forwarding traffic to the local device, even if the routing protocol adjacency is interrupted. The other features, NSF, SSO, and NSR, do not require participation from other devices. They are solely functions of the local device. Okay, let's go to question 2. Which of the following statements about SSO are correct? Select 2. Pause the video now to select the best answers. Okay, the answers are A and D. After an initial synchronization, SSO then performs incremental synchronizations from active to standby, as changes are made to configurations, interface states, etc. And SSO on its own does not preserve Layer 3 forwarding during RP failover. For that, it needs to be combined with NSF. B is incorrect because Layer 2 forwarding is preserved during RP failover with SSO. And C is incorrect because STP states are checkpointed from active to standby. So even if there is a failover, there is no need for STP to reconverge. Okay, let's go to question 3. Which of the following statements about GR are true? Select 2. Pause the video now to select the best answers. Okay, the answers are B, the device performing an RP failover must be GR capable, and D, the neighboring devices must be GR aware. GR capable means the device is capable of performing a graceful restart. GR aware means the device is willing to continue forwarding traffic for a short time to a neighbor that has been lost. That is also called helper mode. Okay, let's go to question 4. Which of the following features allows a router to fail over to the standby RP without interrupting routing protocol adjacencies? Pause the video now to select the best answer. Okay, the answer is C, NSR. Nonstop routing allows a device to fail over to the standby RP without bringing neighbor adjacencies down, preserving the flow of Layer 3 traffic. Okay, let's go to question 5. While configuring an IGP on a Cisco router, you notice the NSF command. What feature does this configure? Pause the video now to select the best answer. Okay, the answer is GR, graceful restart. When configuring IGPs like OSPF, EIGRP, and ISIS on a Cisco router, configuring NSF doesn't actually configure the NSF feature, but rather GR. BGP, on the other hand, uses the correct term, graceful restart. Make sure you're aware of the difference between the two. Okay, that's all for the quiz. Now let's look at a bonus question from Boson Software's XSIM for NCore. Okay, here's today's Boson XSIM practice question. Your company's network contains 2 Cisco Layer 3 switches, DS1 and DS2. DS1 is configured with 2 RPs, and it is directly connected to DS2 by using an Ether channel link. The 2 Layer 3 switches are configured with HSRP. DS1 is the active router. You want the standby RP in DS1 to be able to take over HSRP functions for the active RP if the active RP fails. Which of the following actions will accomplish your goal? Okay, there are 5 options. Pause the video now to select the best answer. And let's check. So you probably got it correct, since we just covered this toward the end of the lesson, but the answer is B, configuring SSO HSRP on DS1. I'll click on Show Answer down here. And here is Bozon's explanation. I recommend pausing the video to read it. Basically, SSO HSRP allows the standby RP to take over for the active RP if the active one fails, without causing any interruption in HSRP. So the HSRP active device remains the same, DS1 in this case. HSRP doesn't fail over to the standby router, DS2 in this case. Okay, that was a quick look at Bozon Software's XSIM for NCore. These are my recommended practice exams for NCore, so check them out when you're preparing for the exam. Before finishing this video, let me thank my JCNP level channel members. To become a member, please click the Join button under the video. Thanks to Velva Jacob, George Streeter, Funny Dart, Nasir Chowdhury, Devin Suku, Gustavo BR, Gerard Baker, Marcel Lord, Pavel M, Mr. Erlison, Dragos Hernea, Zakib Shah, Mayor Salman, Mason Anderson, Vitaus194, Gina Lindley, Mark Jackson, Bold1C1U, Michael Carroll, Gerald Guillaume, Gabriel Braga, Hector Hernandez, Ali Polat, Maratuba, Roji Kuriakos, Arpad Konives, 5 Feet, Owad, Daniel Brown, Tricky Mickey 123456, Scott Thompson, Jose Alvarez, Kevin Hayes, Usain Yavuz, Samuel Tavares, Mustafa Irsoy, Dear Diso, Nasser Zahar, Alexandru Badic, Brian Grant, Georgi Yemejev, Ahmed Ismail, Dibia Swain, Arlen Plagaria, Adlison Pereira, Farad69, Lucian Stoichitoyu, Madmark50484, and Sean Powell. Sorry if I pronounced your name incorrectly, but thank you so much for your support. Thanks to you and my other supporters, I am able to make these videos and release them for free on YouTube, so I really appreciate the support. Another great way to support the channel is to like the video, leave a comment, subscribe, and most importantly, share this video with others. So, if this video was helpful, I'd appreciate it if you did any of those. Thanks for watching.